Hello everyone. In this video, we are going to talk about depth calculation from focus. If you watched my recent videos, I recently published one on how does camera autofocus work. So I showed different mechanisms for cameras to autofocus. Now, can this autofocus also be used to basically calculate the depth or distance of the object to the camera? Is that a possibility? And the answer is yes. Now, here we try to introduce it in simple language. So, how do you do that? So, what you will do is, as you probably experienced, if you are taking pictures of a nearby object, right, you have to have some focal length. And then if you can change that or adapt it, you can focus on an object that is far away. And the question is, can I, now, practically we don't have infinity, but let's say instead of infinity, I don't know, this is like 1,000 feet or something. So can you estimate these numbers by making the focus on those objects and seeing those objects with very sharp edges? Can you estimate these numbers from the focal length that you are practically using? And the answer is yes, you can. So how would you do that? So you try to change the focal length and get a bunch of images from the object. Now, for each one of these images, you calculate a sharpness measure, right? And then you want to find the one that is the sharpest, the most clear edges, the best edges that you can have, the sharpest edges that you can have. And there are different measures for sharpness. So you can use the Laplacian, you can use a modified Laplacian, right, where these second derivatives of intensity with respect to location, they are first you take absolute value of them and add them, or you can take the first derivatives and add them to square them and add them, which is called Tenengrad gradient, or you can use a variance of the intensity, right? So there are different ways that you can measure sharpness of an image. So once you come up with the loss function or a cost function in this case, then the focal length at which this cost function is like the depending on what it is, if it's the minimum or the maximum that optimizes basically this cost function, will be your optimal focal length. And that means at that focal length you can get the sharpest image and the object is in complete focus. Okay, you did that. Now that you do it, how can you possibly measure the distance to the object? Because this is this distance that you are interested in, okay? So the way you do it is simple. You use the law that we know for any lens, that 1 over the focal length is equal to 1 over the depth plus 1 over the distance of the image plane to the lens. So here E is the distance of the image plane to the lens, Z is the distance of object to the lens, and F is the focal point. This simple formula that you probably have seen in physics, this is exactly what you want to have. And in this case, what you can do is really, you can have a fixed F and you can modify E, okay? So if F is fixed and you move your image plane such that your object basically is perfectly in focus, so these lights that are coming from large distance, they can exactly focus at that point, then you can basically do your optimization to find the best E instead of the best F. Okay, so you're using a fixed lens, but you can move the location of the image plane E and find the E that is giving you the best sharpness measure. So once you have E from those optimizations and you have F, guess what? From here you can easily calculate Z. So Z is going to be basically 1 over F minus 1 over E. Or if you subtract, basically it is going to be Fe over E minus F. Okay, so very simple. You can calculate the depth from here as long as you have these numbers. Okay, so this is one way that you can do the depth calculation. Another thing that is also related to this depth calculation is if you have a bright spot here, okay, a bright spot, and you project it with perfect focus, you're going to get a bright spot here. Good. But if you move the image plane now, you are starting to get a blurry image, right? So your bright spot is not going to be a bright spot anymore. If it was already a perfect bright spot, now it's not going to be bright spot. It's going to be basically a kind of blurry circle, and the circle will have some radius r. And the more it is out of focus, the bigger this blur is going to be. This blob is going to have a bigger radius. So the question is, can I estimate this radius? Is there a way I can estimate this radius based on how much out of focus the camera is? The answer is yes. And the simple linear approximation for that is L delta over 2E. And what is delta? What is L in this case? So in this case, L is the diameter of the lens, okay? So if this lens, as we know, is coming from a spherical surface, then this diameter here is L. Now, how would you find the diameter? Diameter of a lens equals to its focal length divided by something we call the focal length number or focal number, okay? So this focal number or focal length number is something that comes with any lens. And if you have that and the focal length you divide, you get L. For instance, they said this lens is 100 mil lens with f of 100 mil and with the focal number 2. What does it mean? It means divide 100 by 2, the actual diameter of the lens is 50. Okay, so you can find L. What is E? E is the distance from the lens to the image plane when it's in perfect focus. So this is when the object is in focus. And what is delta? Delta is the displacement of the image plane from the focused scenario to the not focused scenario. Remember I said when it's not in focus, that's where you have a blob with radius r. And when it's not in focus means the E has changed, has moved a little bit. So E goes from E to something like E prime. The difference between E prime and E is what we call delta, the displacement from focus to not focus image plane, that is delta. And R and delta are related through this linear formula here. So that means the more the image plane shifts, basically, that means the bigger the radius of that blurry blob is going to be, and it's kind of expected. When it's perfect at delta of 0, that radius should be 0, and it should be a single point in theory. So this is a simple approximation, and this formula could also be used if you want to know what happens and what kind of blob you can get. So this can also be used. Okay, so here I gave you this second formula, but the way that you calculate depth is, as I said, through here. And then this bottom one also helps you to find the extent of blurriness if you have to use it. And one thing that we need to mention here before ending this video is, although this method looks great and very simple, the thing about it is the limitation it has, and the limitation is the sensitivity of this method. At the top or the bottom formula, actually, especially the bottom one is, or top one, doesn't matter. They both depends on the depth. They don't both depend on Z. For different Z values, your sensitivity will be different. And what does that mean? So let's say you have a lens with focal length of 0.5 meter and with the focal length number of 2.5. That means your L is 0.2 meters. Now let's consider two different scenarios. Scenario one. First, you put your object at 0.857 meters. That means, based on the lens formula, your image plane distance should be 1.2 meters. So this is what you have, perfect focus object and everything. Now you get the picture of the object out of the focus. How? You move the object. Right? So there are two ways to make the object out of focus. Either you change the camera or you move the object. So let's say here, we move the object a little bit from 0.857 meters, we move it to 1 meter. We change it a little bit. If for this new Z with the same F, we calculate E, your E is now at 1 meter. So it moved from 1.2 to now 1. That means your delta is 0.2 meters, the shift in the E. And if that delta is plugged into this formula, you see that the radius of the blob is going to be 0.02 meters. So the perfect spot that you had here is now going to be a circle with a radius of 0.02. Now, if you move the object further down and now go to 2 meters, shift it for another 1 meter, move it away, E is going to go to 0.667. That means the difference between this number and 1.2, the delta is 0.533. That means you plug it into the formula, the radius gets 0.08. So it gets a little bit bigger. Yes? So you see that although here I do not move the object big time, I only move it first time for like 0.15 meters and then for 1 meter, but the size of this blob is significantly increased. It went from literally 0 to 0.02 to 0.08. It became like 4 times bigger. And you expect that as I change this Z a little bit bigger to like 2.5, 3 meters and so on, the blob, the radius of the blob gets, it changes significantly by the change in the location of the object, although that change is not major. Now I repeat the exact same experiment, but this time I start at 10 meters. First, perfectly zoom at 10 meters, and that means my image plane is going to be at 0.526. So at this 10 meters, I have a perfect, almost zero radius hot spot, right? A bright spot. Now look, I changed it 1 meter again, like last time. E goes only to 0.524. That means your delta is only 0.002 of a meter. You plug it in, your radius becomes 0.0004. So it barely gets any bigger. And you change it another meter, your E goes to 0.552. That means delta from this number to this number is 0.004. That means radius is 0.0008. So again, slightly bigger. Do you see here that the sensitivity here to autofocus, or not autofocus, to changing the position and refocusing is much less compared to when the object is basically closer, right? So when the object is closer, the image becomes blurry very fast. But here, the object does get blurry, but the changes are very, very small. It's not really super tangible. Here, it's tangible. That means when you do your optimization, in this case, here for like Z of, if at Z of 0.8 and Z of 1 or Z of 2, you see here some very perfect images or perfect edges. And here some relatively bad edges or mediocre edges. But if you started at 10 and you went to 11 or 10.2 or something, if this one is a perfect edge to start with, this one is also almost perfect edge. So it's very easy between different numbers where one of them is very good and the other ones are not good to pick this as my best and my optimum location, while when these guys are very close to each other and their sharpness measures are very close, it's not easy. So it's the difference between a very deep valley and something like this. Here, picking this point is much easier than here picking this one. Okay, so the sensitivity of this method is only good when the object is close to the camera. The further the object gets away, your optimization becomes harder, and finding the global minimum is not going to be as trivial. And that is not just for this method. Any other method where the cameras are involved, as soon as the object starts to go further away, you are going to lose all of the sensitivities. The same goes for stereo cameras or any other system. As the object gets further away, their detections are going to get less and less sensitive and harder to do. So just wanted to clarify that for you. So hopefully you learned something in this video, and I'm going to see you in the next lecture. Thank you.